Thank you very much for the invitation. So in this talk, I'm going to explain the so-called Baaz generalization method in the context of arithmetic and also giving some of its applications. But first of all, maybe I should say that this is a method of logic that could be actually applied in any area of mathematics, and the main scope is universal sentences, as you will see with one example. Okay, so I divided the talk in two parts. The first part I will talk about Fermat numbers, because they were the motivation of how this method was discovered, and the second part I will explain the method. Okay, so recall that a Fermat number is a number of the form 2 to the 2 to the n plus 1, where n is a natural number. One property that they have is that they are pairwise coprime. That is to say, they do not share any prime factor. Another, originally by Euler and later improved by Lucas, is that we can always express their prime factors of the putting them of the form k multiplied by 2 to the n plus 2 plus 1. So note, by the way, that in particular they are Pythagorean primes, because if you remember, Pythagorean primes are primes of the form 4k plus 1, and they have interesting properties. For example, one, applying Two's lemma, you have that you can express them in a unique way as the sum of two squares. One odd number, another one even, and of course it's easy to verify that they are also coprime. Yes. Okay, so another very important result is the so-called Pepin's test. That is a characterization of their primality, that the nth Fermat number is prime if and only if we can perform this division here of dividing 3 to the fn minus 1 divided by 2 plus 1. And some of the applications that we made of Baaz generalization methods were precisely trying finding sufficient conditions for a number to be a divisor of a Fermat number. And in some cases, we even succeed in finding a converse implication. So we have another characterizations of primality. And by the way, this test looks intractable, but actually seems to be that computationally there are algorithms that in which it's quite useful. And for example, it is, here I must say that, as you can imagine, because of the double exponent, these numbers are really difficult to handle, and only the first 12 Fermat numbers are fully factorial. And what I wanted to say before, that we know two examples of Fermat numbers that are composite, but not prime factor is known, and essentially this has been proved by using this characterization. So yes, as these numbers are so difficult because of their enormous size, sometimes it's more useful to, instead of proofs consisting in just dividing out, having concrete other kind of proofs that were sorted, and this was how in old times, for example, Euler achieved to prove that 641 was a divisor of the fifth Fermat number in a relatively short way. And this method appeared precisely by seeing that this apparently unconnected proofs, maybe they could have some hidden connections, or at least they could be extended to other values. And so yes, this is precisely the motivation. Okay, here in order to express, to reflect a bit the difficulties that we can have by dealing with these numbers, I displayed another construction of the Fermat numbers starting from the prime numbers. So consider the sequence of prime numbers, that is 2, 3, 5, 7, etc. Then take certain subsequence that we don't know any pattern on it, or yes, and so 3, 5, 17. Then rearrange it by following certain mysterious permutation of the natural numbers. So, for example, the first 4 values remain in its place, but the next 2 get commuted, and yes, they start to get shifted. And finally, multiply certain amounts of consecutive terms. Still, we cannot give information either about how you must form the amounts of consecutive terms. And this is precisely the sequence of Fermat numbers. So here we split the part of the mystery in 3 unknown integer sequences. So some open problems. Well, first of all, are all Fermat numbers square free? Because so far we don't know any repetition of a factor, and in this construction that I was showing, I was assuming that you take each factor only once, but it might happen that in the multiplication step, in the last one, for example, imagine that instead of multiplying 641 times the next number, you have to take 641 to 3, for example. So it never happened before, but it is not proven that this is the case. Like theoretically, it could happen. Next, what I was commenting of these sequences, that they are completely mysterious so far, and any new pattern would be interesting in any of them. So the first one was the indices of the subsequence that we were considering. The next one is the permutation of the natural numbers that, as I told you, the first 4 values keeps in, they are kept in their place, but after that moment, they start to move. And yes, maybe, for example, you could ask yourself what are fixed points or cycles or these kind of things. And in the last one of the amounts of consecutive terms to multiply, only these terms are known so far. So apparently it looks monotonic so far, but Selfridge conjectured that the last sequence is not monotonic. So in particular, it could decrease in some moment even to 1, which would mean that another prime Fermat number might exist. That this is usually the most important question in this area, like why the first values are prime and later no one is known. There are more, or and this is, if this is the case, what is their cardinality? They are only finite or not? Okay, and now I explain Baaz generalization method. Okay, so I will do it with a concrete example that is the Bennett and Krejcik's proof of 641 dividing the fifth Fermat number. By the way, I was telling you that this method is designed to be applied on universal sentences. So in this case, or even with constants, this is in this case, and basically, as you fix the parameters in the beginning, your proof is going to look as a tree. So here we are going to treat it as a tree and tell some instructions for the leaves. So yes, so 641 divides itself, obviously, and we use the property that it can be expressed as 5 to the 4 plus 2 to the 4. We multiply by the right by 2 to the 28. Then we add and delete 1. Here, another branch, we use a property of polynomials that is that x plus 1 divides x to the 4 minus 1. And in our concrete case, we have that 641 can be written as 5 multiplied by 2 to the 7 plus 1, and this instance look as displayed. And using the last two nodes, we actually have that if we apply this arithmetical property, that if we are dividing a sum one of the summands, then we are actually dividing the other one. So we obtain what we were searching, that is that 641 divides the fifth Fermat number, because 32 is 2 to the 5. Okay, and now the method, the first step is that for every leaf, we replace every constant by a variable without repeating them. And there is no need to keep the operations, but we must keep all the other relations. So here we have two leaves. One, we generalize it like this, and the other one like this. Then the second step is that for every implication, replace every constant by a variable without repeating them. And here, you, apart from the relations, you also need to keep the operations that are necessary to justify the step. So for example, in this case, we performed a multiplication by the right side. So we put A1 divided by B1 plus C1, and I1 divides B1 D1 plus C1 D1. Okay, the next one, we added and deleted a quantity. So we express it like this. So here we generalize it one to be yes, any quantity. And finally, the property that I told, that if you are dividing a sum and one of the summands, then you are dividing the other one. And here is the most complicated step, because in practical terms, you have you might have a lot of parameters, and here you have to minimize the number of variables by simultaneously unifying all pairs of formulas that are applied to the same vertex. And by the way, all the relations, and in particular all the operations, must be kept. So here you perform the simultaneous unification of all the nodes, and it looks as follows. Okay, so one application, for example, of this concrete example, we started from this original calculation that 600 divide itself expressed, and we use it also the property that is can be expressed as 5 to the 4 plus 2 to the 4, and also we utilized this property of polynomials, and then we obtained the desired thesis. And the generalization looks simply like this, so maybe it doesn't tell us too much, but now using what you have, you search for a concrete instance of what the problem that you are originally pursuing. So in this case, taking A to B of the form that I told in the beginning, B to the n minus 2r n plus 2, C to the 2r n plus 2, K to the 2r, and E equal to 1, then you have a sufficient condition for a number to be a divisor of the nth Fermat number. And apart from its theoretical interest, this is also computationally interesting, because by varying R, you can make this the number to analyze significatively smaller than the nth Fermat number. So here I give a concrete example in the case n equals 6. So here we have that this number divides the 6th Fermat number. By the way, in this concrete example, you always are going to have the Fermat number as the value of R equal to 0, because as you can see here, the first one is going to be 1, and the second one is going to be 2 to the n. So for R equals 0, we have this division. For R equal 1, we have this, and look at how much this decreased. And for R equal 2, we actually reach the optimal one. So it's way more smaller than the 6th Fermat number. The remaining cases are not so good, but yes. And this is how this theorem looks a bit more formally expressed, and also a conjecture, because this what I saw with here happens in all the examples that I checked, that this number divides the nth Fermat number if and only if for some R with that doesn't make the exponent negative, obviously, we can perform this division. But also, as we saw in the example, it seems to be that if you can do it for some, you actually can do it for every R of this form. But yes, this is not proved still. And other results of this kind. The pioneer one was by Baaz in 1999, and it says that if we are able to solve this Diophantine equation in Q, then we can ensure that this value is our candidate is going to be a prime factor. So yes, so we are having K and N known as input because we are checking candidates. The second one is also another that I see it with certain computational potential. That is that if we achieve, if our candidate divides if the n-1 Fermat number -1 minus PC y square and +1, then our candidate is valid. And I see here this potential because precisely by varying C, we can make this value quite small in comparison with the n Fermat number. And finally, a theorem that this is a characterization actually because Yang Wang achieved to prove the converse implication is that a number is a divisor, a number P is a divisor of the n Fermat number, providing that has this form. If and only if P divides f of n plus 2 minus 1 up to k minus 1 divided by fn. And I think that here in the last line, I should have written n plus 2 instead of n plus 1. And that's all. Thank you.